Hi, my name is Guilherme and I take care of the creating and assembling tasks for Betelgeuse. I also help Felipe and David with small chores to get experience.
For our presentation, we wanted to break language barriers, so we decided to create a robot that could communicate with humans using gestures. With that in mind, we had the idea to mix Chaplin's Mother Times movie with a fun interaction with the robot, where Rigel will keep annoying Chaplin during recordings until he loses his mind and removes Rigel's head. Now I would like to highlight the refined finish of our robot. We wanted to improve from the last one we made, making now a robot that had a professional look. Thus, we chose to go with ACM for our main material. This gives a great look for Rigel, as it is also thin and resistant, plus we also have some acrylic details to give a step up on our visual design. We have well-distributed PCBs, which help a lot in organization and also avoid bad connection problems. Putting it all together, we have a refined, professional and cool design. We were able to mix acrylic and ACM to create a robot that seems integral.
Hello, my name is David Araújo, mechanical and 3D designer for Betelgeuse.
We use a Fusion transistor to design and test the mechanical 3D aspects of the whole League project. To confection our pieces, we use many different machines, such as the lathe to make aluminum shapes, 3D printer to work with PLA and ABS, the laser cut for acrylic pieces, and the CNC to cut aluminum composite material, ACM. Now, one aspect that I would like to highlight about Rigo's mechanical system is the arm mechanism. Basically, the biceps and forearms work in two independent shafts, consequently they have independent motors. The biceps motor is coupled on the Rigo surfore and makes the shoulders movements. However, the forearm movements is a way more funny because it comes from an untypical position inside the body. But why is internal and not coupled on the Rigo's shoulder? Despite all the calculus and mechanical adjustments are simple. We are looking for a compact, fast and spry robot, so we put in a position that reduces the torque impact of the motor's weight on the system. Our robot is a long gear transmission torque arrangement to make it possible. The forearms motor can stay inside the body and still make external gesture, which reduce the appearance size and increase the functions of Rigo.
Hello, I am Felipe Dornelos, electrical and software designer for Betelgeuse.
For our project, we had a huge diversity of concepts regarding software and electrical aspects. We are using two Teensys 4.1, one Arduino Mega and one OpenMV 87 Plus, and there is also an AI running on the glove, which means that there are 3 different microcontrollers and 3 different coding languages, C++, Python and MicroPython. For the PCBs, we also had a lot of diversity as we worked with many different components and strategies, such as double-sided PCBs for instance. One thing that I would like to highlight is the glove project itself. We think that this was the perfect fit for our initial idea of breaking language barriers. In the glove, we have 5 MPU 6050 modules to read the movement of the user. We are using the Euler angles concept to analyze the movement through the 3D Euclidean space by evaluating the pitch and roll angles shown in the figure. Another strong point of the glove is the random forest system, which is basically a method for classification by building multiple decision trees during the trainment. After that, whenever an input is given to this system, the trees will vote on what they think that is the correct output, and the most voted one will be the answer. Then, this will be sent via Bluetooth 5.0 to the body that will do the same with the head. Both of those last parts of the robot will then give a feedback for the respective given command. Last but not least, our final focus will be on the movement of the robot. We have designed a trajectory generator system in which an imaginary Cartesian plane is made where point 0, 0 is the position of the robot at the start of the trajectory, and the other points on the x and y axis are the distance traveled horizontally and vertically. There are also a lot of other parameters that we can adjust, such as this distance parameter where we choose if we want the robot to do a tangent shaped trajectory or just try to do something more straight. We can also change, for example, the variables of time and speed for each sector of the trajectory. This kind of system is similar to the ones used on drones, but ours does not need to worry about the z-axis as Rigo unfortunately does not fly.
Now, focusing Rigo's mechanics, for this type of movement to be possible, we use the stepped shaft, which supports a bevel gear counters, a pair of spur gears for the encoder and wheels. It is important to highlight that each mechanic was calculated and approach for a lowest motor stress and tension between the practice layers.
Thanks for the attention, see you at Eindhoven, bye!